All right, we're still working on our solution to the area problem, which is what's the area under a graph from point A to point B. And the big solution to that problem is an antiderivative, just as the solution to the tangent line problem was the derivative. Taking what's called an antiderivative, which as you might guess is just the derivative process backwards, that's going to be how we find perfect areas. We're not quite there yet, but we're going to learn. We're not going to find the perfect areas yet. That's our next step, but for right now we're going to talk about how to take some antiderivatives. Now this, just to get some terminology, this top expression, this is called a definite integral. A definite integral has limits of integration on it, and the result of this is a numerical area. Just say it results in a number. It's technically not always the area. Sometimes it's negative and above and below the axis. We'll get into that some. But the answer here is a number. And we've talked about a few of those where we've used geometry to find the areas of the shapes. But for right now, just know that's a definite integral. This next one is an indefinite. And both of these involve what's called an antiderivative. Now, the expression inside my integration symbol, x squared plus 2, that would be the derivative if the starting function were x cubed over 3 plus 2x plus any number, any constant c. We're going to talk a lot about that constant c. But if you worked backwards, that's the antiderivative of x squared plus 2. Now, antiderivative and integral, they're not by the book the exact same thing, but they're pretty much used interchangeably. They're just the opposite. They involve, calculating an integral involves finding this antiderivative and then moving from there. If you look over here, just to confirm, this x cubed over 3, this term, if you were to take the derivative, the 3 would drop to the front, and it would cancel the 3 that's already there, and then it would decrease to 2. And then if you take the derivative of 2x, you just get 2. So we're left with x squared plus 2. And this plus c just means if I had a plus 11 there, the derivative of that is 0. If I had a plus 55 there, the derivative of that is 0. When we take antiderivatives, we're going to put a plus c on the end of them to represent the fact that any constant could have been there. The derivative of that is 0. And that means there are infinitely many functions that could serve as the antiderivative of a function like x squared plus 2. Okay, so just like when we started derivatives, we started with the power rule and then we moved on to the basic trig rules. The power rule for antiderivatives is just the way we undo the process of taking a derivative. It's the opposite. Instead of dropping the n down in front and decreasing it by 1, we're going to increase it by 1, make it x to the n plus 1, and then we're going to put an n plus 1 in the denominator. So you can see how if you reverse that process, the n plus 1 would drop down. If you took the derivative of this, the n plus 1 would drop down and cancel out the n plus 1 that we just added to the bottom. That's why you have to add it to the bottom when you're doing an antiderivative. And as always, plus c. So this power rule, for at least early on and really throughout all antiderivatives, you'll use the power rule 90% of the time, I would say. So our first little simple example, x cubed, the antiderivative of x cubed is x to the 4th over 4. All right, the 4, if you were to take the derivative of this, you get x cubed, so that's why it's the antiderivative. Now a lot of these, because x cubed becoming x to the 4th over 4, there's only so many easy examples like that we can do. A lot of these are going to be kind of weird powers, just like they were with derivatives. The integral of the square root of x is the same as the integral of x to the 1/2. So now that it looks like a fraction, 1/2, it's simpler to apply the power rule. It doesn't matter if this is a whole number or a fraction like a half, we're still going to apply the power rule. We're going to add 1 to 1/2 and get x to the 3/2, because 1/2 plus 1 is 3/2. and we're going to put that over 3/2. Whatever that exponent is needs to get put on the bottom. And a lot of times we'll write that as 2/3 x to the 3/2 just to not have a fraction underneath in the denominator, so we'll move it out front and make it 2/3. And this other one, this next example, if you have a rational expression where you have two terms on top and one on the bottom, you can divide it up into pieces. X to the 4th over x squared is x squared. X square root of x, which is, remember, x to the 1/2, over x squared. You're subtracting exponents. X to the 1/2 minus 2 is negative 3/2. And there's the two power terms, power rule terms we can integrate. We can find the antiderivative of. And when you have two parts, just like with a derivative, just calculate them separately. The integral of x squared is x cubed over 3, and the integral of x to the negative 3/2, that would be x to the negative 1/2. Okay, be careful with your adding and subtracting from negatives. Negative 1/2 plus 1, excuse me, negative 3/2 plus 1 is negative 1/2, and then whatever that exponent is needs to get put down here. So if we simplify that, we get x cubed over 3 minus, because we've introduced a negative sign here, and I'm also going to move it to the front. Actually, I'm going to do a couple things. I'm going to make it minus 2, because a 1/2 on the bottom is the same as a 2 on top. And I have x to the negative 1/2, which I'm going to move to the bottom because it's negative, and make it a square root because that's a little bit cleaner version of a final answer. Plus c, and there's my answer. And I'm noticing as I worked my last one, I forgot my plus c, mostly because I ran out of space. But don't forget that plus c. It's something that's sometimes easy to forget, but it's important to include a plus c every time. So there's some power rule examples. And just so you're, we've talked about this when we talked about definite integrals introductions, but any of these, like let's say x cubed, if I had 2x cubed, that 2 is just along for the ride, and whatever else happens, that 2 will be a part of the answer. So 2 times x to the 4th over 4, or x to the 4th over 2 plus c. So constants we've sort of addressed in the past, but just so you know, any of these with constants worked in, those constants just tag along and they're part of the answer. You could actually pull it out to the outside if you're more comfortable, get it out of the way, and then just worry about it at the end. So this is the power rule. Let's get to some trig. Okay, so we're going to learn 6 antiderivative trig formulas. But before that, let's, because they're completely based on the trig derivatives that you should know. So take a moment and see if right now you can remember your 6 trig derivatives. It's something that you probably memorized at some point, maybe you've forgotten, but take a moment to review those. You can pause and try to write those down. I'm going to pause and reveal the answers. Okay, so there are the 6 trig derivatives that you learned a long time ago. Those 6 reversed are the only 6 trig antiderivatives that we're going to learn for now. We can take the integral or the antiderivative of cosine and sine and secant squared dx and cosecant x cotangent x dx, and you can get the picture here. We're just reversing the 6 formulas. I'm going to leave the negatives as part of the answers, like that negative on cosecant. I'm going to not put it here. I'm going to leave it as the answer, just so these are all positive, and then we can just figure out which answers are negative, which antiderivatives are negative. Now there is such a thing as the antiderivative of tangent x. We just aren't learning it yet. It's based on a little bit more complicated process. So as of right now, the only trig derivatives or antiderivatives that you need to know are these 6 specific formulas. So these 6 you need to, and if you remember your 6 derivatives, then these are easy. The antiderivative of cosine is sine. And we need to add a plus c, because if you're going to take the derivative of sine x plus 4, you would get cosine x. Sine x plus pi, you would get cosine x. Whatever constant, that's that c popping up again. Now, the antiderivative of sine is negative cosine. These negative signs, the one here and the one here, are often ignored or forgotten, so don't forget those two. The antiderivative of secant squared is tangent. The antiderivative of cosecant cotangent is negative cosecant x plus c. Secant tangent becomes secant, and cosecant becomes negative cotangent. So, just like with derivatives, early on we learned only the power rule and these 6 functions on the left. As of right now, for antiderivatives, you need to be able to complete a power rule and these 6 on the right. That's all we need to know for antiderivatives at this point.